sorry, I just want to correct something. So that is, so actually this just a statement. If yeah, all the statements are also okay, but for later purpose, actually, instead of this, I consider this. So maybe I start from this again. But before that, maybe I just give another correction. So, sorry, this. So correction is about these things. Maybe I wrote this thing, right? So in fact, I consider the following. So I have this lambda, and yes, I have this lambda 0, and then I have this z1, zm, and then going to this lambda of this y1 plus minus 1, or the yn plus minus 1, and then here, probably I didn't really define this before, but here I have 0 here, and then p circle, pp here. Okay? So I didn't define this, but this one is somehow sum of ai and yi, so that if I take a variation of ai, and then sum of this ip, up, p runs from 1 to n, this certainly goes to infinity as goes to infinity, but also assume that this term is actually non-negative for all this u inside of p. Okay? So sorry, this also for p, for any p, for any u from p. Okay, so we consider this. So we already discussed this without 0 here. But if I have 0 here, actually we add this condition. So, okay. And here I have lambda 0, not lambda, and here I have lambda, but here I put this lambda p, 0 and p. So this is rather strange notation. In fact, in our second paper, we use maybe this notation. But it looks like certain power series over this ring, but no such ring exists. So therefore, instead of this, actually, we change the notation from here to here in our third paper. So therefore, now I use this. So this is the p case, and same thing for this. So this is the same. Instead of this, here we just assume that u is any element from the integral of this polynomial, and then you can define this. So I didn't really define this, and then the next one is okay. So I consider lambda z1 that zm. I defined it, and the definition is okay. And then this one is surjective to this lambda y1 plus minus 1 yn plus minus 1 of p. So this one is defined without this last non-negativity condition. So that I already defined. So this is also okay. This is surjective map. But then I consider, so the correction is here. What I wrote was something, this goes to so I wrote something like this, but this is not correct. So therefore, at that time actually I said that maybe, so I may make it more precise later, but maybe I should do this. So here I take lambda 0. So it's a sorry, this is actually just a power series ring, usual power series ring over lambda 0. So actually I wrote this way. But the correct thing is lambda 0 of this tensor with lambda over lambda 0. It's a field fraction of this. And then we have this, and this is surjective. So the correction is this one. Correction is this one. The point is this one. This one is not equal to this lambda z1 zn. So this is a little bit, yeah, if you look at the definition, certainly you must know this. But this is different. And for this one, actually, for this one, lambda 0, z1, zn, and then tensor lambda 0 and lambda, and then this is actually small, it is equal to lambda of z1 to zn. But this one is not. So this is a little different. So actually, this should be the correct one. So this is one thing. And the second correction is here. So I may start from here. Okay. So just this one is not correct. Instead of this, I put this. Okay. So this is a little bit strange thing. So yeah, if I have this or this is rather standard thing, but other one is not so standard. Okay. So this one is just like this. So now I consider the case that Q and Q prime are homologous, right? And then I denote by P, it is a difference. But difference is actually boundary of something that we wrote R. So this is a chain. And then I consider modular space, this ML plus 1 and K plus 1, beta. And here I consider any torus invariant cycles, and finally I put this R there. So here I can put any torus invariant one, so like a P1, that is a PL. They are all torus invariant cycles. And then finally I put this R, right? I consider this. So somehow more general than the previous one. And then consider its boundary. So the boundary of this guy. So boundary this Y has 3 types. So first one is this M L plus 1, K plus 1, and beta, and P1 the PL, and then boundary of R. So this is one thing. And second type is this M L1 plus 1, L1, K1 plus 1, L1, K1 plus 1, of this beta prime, and here I have p something, so maybe p sigma 1 p sigma L1, yes, and then tensor product of L of M L2 and beta double prime, and here maybe p, I don't know, maybe sigma L plus 1 p sigma L plus L1 plus 1 and L1 plus L2, and finally I put R here. So sigma is actually a permutation. So sigma is actually permutation of L1 plus L2. So they may shuffle. And third type is Fm L1 plus 1 and K1 plus 1 and beta prime and P sigma 1 P sigma L1, and finally I put R here, and then take the phi output to L and M of L2 plus 1. Sorry, L2, this one is L2 plus 1 and K2 plus 1. So L2 and then K2 plus 1 or beta double prime. And then here I have P of sigma L1 plus 1, P sigma L1 plus L2. And then finally, this is it. So we have three types. And for our purpose, after we consider this P1 to PL are all some bulk class. Yeah? So I started from some bulk class, so therefore I start from this. So take B, and then B may be a Poincare dual of something. So I may just denote by B check. And then later we need to consider P1 PL equal to this B check, everything B check. But anyway, so this is just I explained before, just picture, and then this P1 to PL maybe just to permute it somehow. But anyway, you get this. So the first one, the first type, certainly this is actually M of L1 plus 1 K plus 1 of beta and P1 Pk, and then finally a PL, and finally I have this Q, and then somehow minus. So it's a space, so therefore it's a disjoint union of this and this, but the second term is actually orientation reversed. So this ML1 plus 1 and K plus 1 and beta and P1 Pk, PL, and then I have Q prime. Okay? So this sort of stuff. So if this P1, PL are all this B check, then so this it contributes to this Kodaira-Spencer tilde of Q minus Kodaira-Spencer of Q prime. Okay? So if you consider the case that P1 to PL or all B check, and consider the whole sum them up over beta, and then use this kind of iterated integral things, then you get this. So somehow, so this one is somehow we want to see, right? So we want to study this. Sorry, this is Poincare dual of this. So this is Q prime as Poincare dual class. Sorry. But anyway, so the first one is this. And second one, if you consider this, yes. So this one, if this P1 equal to PL equal to B check, then it contributes to the following. So this one is actually some kind of M operation. Yes, M operation deformed by B, and then you may have some element here, and then this one is also a Q operation, and yes, and here maybe B with power. Okay, so Q maybe something, maybe L prime, and then take R, and yes, and something like this. So this one is coming from here. So if all of them are B, then this one also contribute to somehow, maybe better to write it. This is also bulk deformed Q of R, something like this. So here, actually, we put the cohomology classes of the Lagrangian torus fiber. So here, this all cohomology classes of the torus fibers. And so we have this. But anyway, yes. So this is something. This is actually something. And then we have this. So this is the second. And third one is kind of opposite. So here we have this. So therefore we have these Q things. And then we have some B things. L1, tensor R, and then I have something here, and then tensor with this M. So this is actually, so if all of them are B, then this is actually MB of something, and then we have this piece. Okay, so we have, yes, sorry. No. This is okay. Sorry. Like this. Okay. So all P are Poincare dual to B check. So therefore, it contributes to this MB check, MB. So therefore, this one, this. And then here I have a bunch of this, and that is also coming from here, but also this. So anyway, so we have three kind of terms. And then I want to say that the third one doesn't really contribute if you consider the case of H1. So if I take element from H1 of this from B here, and then consider then I consider the third case. So that is actually Q, and then this B L1, and then R, and then maybe B tensor B, and then here I have this MB of B B, and then tensor B tensor B, something like this. But we know that this one maybe MK2 and Q, yes, KL1 plus 1, K1 plus 1 or something. But anyway, so this one is proportional to unit. So if everything is just the H1 and no R appearing here, So therefore, in the previous argument, this one is actually proportional to the unit. And so therefore, once you have unit, if you are perturbation, if you are, in this case we have to use certain perturbation, but perturbation is somehow compatible with forgetful map. So there are something, and then this one vanishes. So this one, because of this one may be 0. So if you have unit inside, then somehow they actually die. So this one doesn't really contribute. Now how about this? Second one. Second one, actually it contribute to the following term. So that is MB. And here I have B. And then here I have this Q of this B tensor L2, L prime, maybe anything okay. Then here I have R. And then here I have again B tensor B. And then again B tensor T. Right? So like this. Okay. So this is something. This is something. Okay. So we started from torus invariant differential forms, but because this is not torus invariant, so therefore this output is not torus invariant. So therefore what we get is not really torus invariant. But somehow, so we have a differential forms here. And then here I have a torus invariant forms. This is equal to the harmonic forms with respect to the torus invariant metric, Riemannian metric. So here, certainly, because it's a harmonic form, so therefore you can just embed it here. And in this case, actually, we also have a projection. So this projection is actually given by average over the torus action, right? So you just take average over the torus action, and then you get torus invariant forms. And so our operation can be compatible with this. So therefore, if I take here maybe harmonic projection, maybe pi here. So if I take a pi of this, yes. If I take a harmonic projection of this guy, so those are all torus invariant differential forms. And this one is the only one which is not torus invariant. So therefore, somehow we can just put it this B tensor data B and pi of this Q of B tensor L2 tensor R, and then B tensor data B, and then again B tensor data B, something like this. So it's just taking average over the torus actions, and so now I may just put it something psi here. So this psi is now torus invariant, right? Because I take a average over torus, right? So then this one is exactly this one, right? So this is first bulk deformed by both B, and then rest are all B's. Sorry. So sum them up. Maybe arbitrary number B in front of this, and arbitrary number B after that. So if you sum them up, and then you what you get is this. Okay, but we know that for if you consider H1 over H1, and then over H1, this M1, even any bulk form this, and this is something related to this the partial derivative potential functions, right? Maybe BB, sorry, B. And then maybe, yeah, B at B. I mean, what I want to say is this. So, this, more precisely, I consider M1 B of EI. And then this is equal to the B at E. Right? So this, and then unit, sorry, and then unit. Something like this. So if you have, yeah, if you consider this on H1, then this is somehow written in this way. But Xi may not be one form. But as we know, we have a kind of Leibniz formula. So if you consider the product of them, then yeah, you have something like Leibniz formula. So therefore, from here, you can see that from these things, you can see that our this M1 BB of Xi is actually lying in the linear combination of, yeah, I mean these things. So dPO, dXi, and B at B of H. So maybe I have to take sum over this I equal to 1 to n of H star of SLU, every lambda 0 something. So we have this. So the first one contribute to the difference of these image of Kodaira Spencer maps of Q and Q tilde, Q and Q prime. And second one doesn't really contribute. And third one actually may be written in this way. So if you combine them, then you can see that this is in this, there's something over this. Of H star of something. But on the other hand, this one is a the direction derivative of potential functions. So it's a function, so it's only a multiple of this. We know that these are multiple of the unit here. So therefore, maybe we can say that maybe this one is actually contained in this. So this is the idea. And so more or less I got a statement. Namely, I wrote the diagram here again. So here I have a case tilde. It takes values in this. This y1 plus minus 1, that is yn plus minus 1, and then maybe 0 in P circle. And then if you just take its cohomology class, so namely you just identify cohomologous toric invariant cycles, and then it actually descends to a map here to this lambda y1 plus minus 1, yn plus minus 1, this, and the modulo of this. B something. Then certainly if we take a closure, then this is B. So therefore we have this map. So this is our mapping from the cohomology to this Jacobian rings. So we define it as Jacobian rings. So why this is related to this? Maybe it's not necessary to say this, but so it's a logarithmic derivative, right? So if yi equal to this yiu and t to the ui, right? So this is what I wrote, and so and also yiu is equal to the exponential of xi. So therefore, if you want to differentiate ddxi, maybe b here, this is equal to yiu and dp of b of dyiu. So yiu is a variable, and so you have this. But then, because of this, so only this one is multiplied to this. So therefore, this is also equal to. This is also equal to. Yeah, but so I denote the same POV as a function for yi and a function for xi. So therefore, it may be confusing, but yeah, just change the variable somehow we do this. So therefore, I have this. Okay. So this is our map. Then I may tell you a bit about these things. So this case is from cohomology from here to this jack of this. So here I define this actually quotient of this ring, and that ring is actually a lambda 0 algebra. So they are actually lambda 0 algebra. Right? So this is actually lambda 0 algebra. Okay, so maybe they both are lambda 0 algebra, and easy to see that this is actually lambda 0 module homomorphism. So this is actually just a linear extension. Linear extension. So therefore, this one is not easy. And then lambda 0 contains its unique maximal ideal lambda plus. So the exponent all really positive. And also if we consider lambda 0 over lambda plus, this is actually just a constant term. This is a complex numbers. So now we can also consider this one, and then going to like this. So this is usual cohomology. Right? And here actually I modeled by lambda plus part. So somehow here again some constant term is only thing we have, and this is actually maybe isomorphic to this C over Z1 Zm. Maybe this is Z1 Zm. So maybe better to write C of y1 plus minus 1 yn plus minus 1, and then modulo this quantum Steiner rational relations. So that is this d P of x d yi, yi, but modulo this lambda plus part. So only look at the lowest order ones. And so this one is somehow Stanley-Reisner relations. Sorry, linear relation. So this is a linear relation appearing in the presentation of Stanley-Reisner rings. And this corresponds to linear relations. And maybe I have to remind you the following. So what is known is that the quotient of this one by linear relation and Stanley-Reisner relation is actually isomorphic to the cohomology of this. Yeah? That's just a classical cohomology. And another thing is, if you consider C and Z1, Gm, I'm going to this C of y1 plus minus 1, that is the yn plus minus 1. And then if you mod out by Stanley-Reisner relations, then this is actually isomorphic to this. So if you mod out by Stanley-Reisner ideal, then you already get this. So then you consider linear relation here and the image of linear relation ideal here. But that is actually written in this way. So this one actually is really the isomorphic to the classical cohomology. So actually this map coincide with these things. So therefore this is isomorphism. So this is isomorphism by classical description of the ordinary cohomology of the toric manifold. So we know this. So modulo lambda plus, it is isomorphism. And then if you have element here, and then look at the lowest order term, and then there is something here which hit this lowest order term. Maybe this one hit not only lowest order term, maybe something else, right? Because it's only after modding out by lambda plus. So therefore, lowest order term is actually image of something, but it may also have a higher one. So anyway, you start from lowest order term, it can be killed by something. And then next look at the next level, and then there is another thing here which hits this. So this is by induction of the exponent of t. Actually, we can easily see that from here, this Kodaira-Spencer map is kind of surjective. So surjectivity is not so hard. And the second thing is maybe this one is in fact a ring homomorphism. So second thing is, so this Kodaira-Spencer map is a ring homomorphism. So I just draw some picture and then tell you a little bit about this. So I consider the following things. So I don't know. So this picture may be a little bit strange. So here I have a sphere here, just a Riemann sphere here. And then I have some disk here, which actually meet here. So disk and P1. And then here I take 1 point here and 2 points here. So this is a border Riemann surface with connecting boundary, genus 0, 1 boundary mark point, and 2 interior mark points. Okay? So this is actually something like this. So you can smoothen this node, and then you are here. And so this is actually just a disk with one boundary mark point and two interior mark points. So if you choose one of them, maybe the first interior mark point, and then you look at this, then you can just conformally equivalent to the disk, and one mark point is just at 1, and the interior mark point is just the origin. So we can normalize one interior mark point and boundary mark point in this way. And so therefore this one is parameterized another mark point here. So therefore such a moduli is in fact again disk, right? And in the middle, what happens in the middle? So if this one approaches to the origin, if they are getting closer and closer, and then you can see this picture. So this one is actually over here. Okay. And another extreme maybe, yes. So yes. And then, yes. So, but we also have the following picture. So I have here disk, and I have one disk here, and then I have one disk here, and then I have mark point here and here. So this is another configuration of bordered Riemann surface of genus 0 with connective boundary, two interior mark points, and one boundary mark point. Right? So here, this component has three boundary mark points, boundary special points, but disk with three boundary special points, actually, the moduli is just 1 point. So any 3 point can be put in a standard. Yeah, these are related by conformal transformations. And this one is this component is one interior mark point and one boundary mark point. So therefore, as I told you here, it is also unique object. So this one is stable, and this one is stable. This one is stable because we have these special points, right? So this one also in this moduli. So I have to see how they are. But yeah, so maybe it looks a little bit difficult if I have this. So it depends. It depends how this point converges to this point. Yeah. But anyway, so yes, because yeah. Because here I have one point here, and then here I have another mark point here, and then I have another mark point here, right? So, for instance, if this mark point getting closer to this, then these 2 points becomes these 2 points. So this origin and these 2 points lie different component. So if this, and you have this. And next, maybe you can move this mark point to somewhere. And now you have 2 mark point and this mark point, and so therefore in the end you have this. Right? So it's a little bit different, but difficult, but somehow if you just consider such a limit, and then you consider another limit, and then you get this. So you have such a thing. So this is just a moduli of Riemann surfaces. So anyway, so these two after smoothing of boundary nodes here, you get this one. So just one component with two map point in the interior and one map node boundary. And if you smoothen this node, interior nodes, you also get this. So therefore, you have a path joining this and this. Okay? So quantum cohomology is something to do with this P1 with 3 map points. Okay, so if I consider this, yes, B1. No, I don't know how I do this. Maybe A1, A2. Okay, so I have A1, A2, both from this cohomology of this, and then this quantum coproduct is something like this. So here we have a aberration map to the target, and here two inputs are just A1 and A2, right? Maybe I have to take Poincare dual class of this. So anyway, you consider such insertion, and then the output is actually the output something like this. Okay, so this is a quantum product. So therefore, if I consider holomorphic map from here to this X with L, then the first part is somehow quantum coproduct, and then you just insert a result in this, and then that is somehow what we wrote this Q or something. But anyway, so I will explain it a bit. And from this side, and I have here, and I have here the 0. So it is our output F0 to L, right? So maybe better to make it bold because it's an interior relation. But anyway, so like this. So now we consider several things, like just take B from A to 1 of this. Now I consider this torus fiber. And then B from this cohomology over here. And now, not only this, we may have more points. So maybe I just use some color here. Okay, maybe blue ones. So I may have lots of insertion B here, or maybe B here. So these blue points, yeah, Poincare dual B somehow inserted. And then we have small b actually corresponding to these. In fact, we actually pull back b at these mark points and then use this iterative integral to do something. But anyway, so pictorially, this is like this. And then maybe it is more complicated. The moduli space may be more complicated, but somehow I also have here the things are maybe a bunch of blue things and a bunch of blue things and a bunch of blue things, and then several things. I don't know. Anyway, like this. So all of them are B's. And the other one is actually this Poincare dual class. Okay. So I consider holomorphic map like this, and here also we consider holomorphic map to this. And then somehow we have some more bigger moduli, one-dimensional bigger moduli space. So namely I have M and L and K plus 1 beta. So this is a moduli space of stable maps with L map, interior map point and K plus 1 boundary map point. And then we just take the domain. So take the domain. So forget maps. So forget map. Forget the map. The stable map. Sorry, so map. And then contract unstable component. So there may be some non-constant component, but if you forget the map, then this component domain is just P1 with 1 or 2 map points, and then they are unstable. So then you just contract. So in this way, you get a map to the just a moduli of border Riemann surface. And then further you forget other map points, just going to M1 of, M1 K plus 1. Yeah, K plus 1. Sorry, L2, L2, okay. L2, K plus 1. So at the beginning, I may have many interior mark points. That is actually blue mark points and white mark points. Here I have also blue mark points and white mark points. Just forget blue mark points. Then we have only 2 white mark points. So that is this map. And even we can forget the boundary map point except the first one. So I still forget about this M2, 1. Okay? So K equals 0. So 2 interior marked points and 1 boundary mark point. And then that is a story I explained before. So this is actually real 2-dimensional things. This is real 2-dimensional. And then I pick 2 special points in this. So maybe I have this kind of moduli, and then some points that are the special point. Then actually I pick some path like this. And then over here I have this one. Over here I have this one. Okay. Then so here I have an interval I here. So interval I over the origin we have this. Over here we have this. Then I have here I. Then I consider the full inverse image of this. So this one is now kind of cobordism of the inverse image of the boundary of this interval. Over here you have this. Over here you have this. And then if you look at it, then now I have more mark point here. So therefore it contributes to this big quantum cohomology, or maybe bulk deformed quantum product. So that is this output. And then we put it there. So then I have this Q here, and then we have bunch of ball B, and then I will also have this one, and then bunch of B's. So this is this side. So this one contributes to this potential function of B plus epsilon of A1, A2, B, and then the epsilon, and the epsilon goes to 0. So namely this one is actually the Kodaira-Spencer class, Kodaira-Spencer image of this A1 B of A2. And from this side, we have such a thing. So this is again this Q of B, I don't know, maybe L1, many of them. And then I have a bunch of B's. Then I have again another Q of B tensor L2 tensor B da 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 B. And then B da 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 B. And then I have this Q of B tensor L3 tensor B and B da 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 B. Something like this. Yes. So this L1 is, so number of L1 mark points. And here I have L2 mark points and L3 mark. Sorry. I forgot one more. So here I may need to put A1. Sorry. I may put tensor A2. So here maybe A1, A2, and this maybe A1, A2. I just keep the argument for discussion for sign. So then you have such things. Okay. So this one, this actually contributing to this potential function of B plus epsilon A1, and then the epsilon goes to 0. Something like this. And this one actually contributing to this dd epsilon going to 0 of potential function and B plus epsilon A2. So namely, this one is a Kodaira-Spencer map of A1, and this is the Kodaira-Spencer image of A2, something like this. Okay, so actually they are unit. So they are actually proportional to unit. They are proportional to the unit, right? And if you have a unit, then if there are other B's, then it must vanish because unit has such a property. So only remaining term is that this one never exists, this one never exists, this one never exists. And moreover, if it is unit, then there shouldn't be any non-trivial element here. So L1 must be 0. Otherwise, it doesn't contribute. So it's all actually coming from the property that they are proportional to the unit. So therefore, only remaining term is actually this M2 of this. So Kodaira-Spencer of A1 and Kodaira-Spencer of A2. Maybe Kodaira-Spencer of A1 and unit and Kodaira-Spencer of unit, something like this. And so, yes, because again this is a unit, so you don't have any quantum contributions. Again, this is proportional to unit, so this is proportional to the unit, and so therefore it is actually just a classical. Okay, so therefore one side we have a Kodaira-Spencer image of the quantum cup product, and the other side actually a product of Kodaira-Spencer images. So therefore what we get is this, right? Actually, this one also depends on bulk class. Maybe I have to write bulk class here, and bulk class here, and bulk class here. Okay. So Kodaira-Spencer bulk class of this A1, A2, B is equal to Kodaira-Spencer map B and A1, and Kodaira-Spencer map of B of A2. So therefore, it's a ring homomorphism. So this is just a rough idea of this. And in fact, so actually, yeah, I may somehow, yeah, have to modify this version a little bit because here, actually, yeah, it is something related to the transversality of this, of the modular spaces. And so if you have non-constant holomorphic map, and then there are some way to perturb the modular space so that it is transversal to these Poincare classes. But it happened to be a trivial class. Then this is a constant map. So classically, this product may be zero. Like if you have a point class and point class, and then yeah, this yeah, just a constant map to that point, yeah, may contribute to this. But this is not really a classical intersection product. So in that sense, somehow, I have to use a little bit topology. So X is a compact toric manifold. And if you have take A1, A2, they are from the cohomology of X. Then maybe there are somehow A1, A2, maybe torus invariant cycles. And so that such that this A1 is equal to Poincare dual of A1, and A2 is equal to Poincare dual of A2, and A1, A2 are kind of transversal. So I take this A1, A2 at Poincare dual of A1, A2 with this property, and then use these inputs as such A1 and A2. Then the classical contribution is nothing but the constant contribution here. So therefore, we can actually complete this argument. I think this may be necessary. This must be. So in our book, actually, we didn't really discuss this, but it may be necessary to really do this. I noticed it maybe last winter, so maybe there may be some other way to argue this. But anyway, so this is the argument. And then, so important thing is this Kodaira-Spencer map is in fact injective. And this one is rather complicated, so I can't really tell you the story. So in fact, we first prove some sort of versality of these things. So as I said, so this one gives the deformation of potential functions. And this deformation is universal in the sense some sense similar to the one I explained in the morning. So using that and a little bit more, even though we have potential function, it is actually a infinite. Yeah, infinite. It may have infinite terms, infinite series, but after a certain type of coordinate change, we can make it into a Laurent polynomial. So this is a little bit argument. But this part is not so hard. In fact, we only use the surjectivity of the Kodaira-Spencer map, and basically, so then actually we can do such things. So it is like a universal family, and we can show the algebraization of potential functions, so that becomes a Laurent polynomials. And still we need to take a closure of the idea. But anyway, then you can just have usual commutative algebra we see often, right? So like a affine scheme and so on. And then here, next thing is somehow we use the work by McDuff and Tolman. So they use the Seidel homomorphism to describe the quantum cohomology of the toric manifold. At least they did it for Fano case. And in non-Fano case, because we have to take a closure, so that part is missing in their work. But so anyway, we have this. And then we have the following thing. So here we have following thing. So we have a quantum cohomology here, right? And here we have this lambda, I don't know, maybe G1 GM. Maybe better to write this way, G1 GM. Then quantum Stanley-Reisner relations. And then some sort of deformed linear relations. So this is actually a bit different from other people. Other people want to keep the linear relation and then deform quantum Steiner-Reisner relation. But in our case, I have somehow this. And this one is actually isomorphic to this lambda of y1 plus minus 1, yn plus minus 1. And then, okay, by this, by certain, yes, by certain, there exists certain number p to pm. No, p to pn, sorry, p to pn. So same numbers, and then take its closures. So this is deformed linear relations. And this pi is congruent to the partial derivatives of yi mod maybe lambda plus times this lambda 0 of y1 plus minus 1 over yn plus minus 1, something like this. And so maybe I have to also put this. And so somehow we have these two relations, right? So if you remember, so Kodaira-Spencer map is a map from here to Jacobian ring. So that is somehow what we wrote y1 as yn, maybe plus minus 1 plus minus 1, and then 0 p cycle, and then this something like this. Okay? So this is Kodaira-Spencer map. So we don't know whether this is isomorphism or not. But on the other hand, using Seidel homomorphism, actually this is actually isomorphism. That we know. So therefore this is isomorphic to this. And this one are not, we don't know whether how they are related. It happened to be equal, I don't know. But anyway, their leading order terms are the same. So we consider the following things. So somehow we consider one parameter family of rings. So namely, we introduce maybe another parameter S and consider the following. So maybe something like this, y1 plus minus 1 and yn plus minus 1. With this thing, maybe 0p. And then also I put this S here. And then modeled by these things. So here I have Pi, then maybe 1 minus S of Pi, and then here I take S times this Yi and dP of Y, dYi or something like this. So if S equal to 0, then it becomes this one. And if S equal to 1, then we have this one. So we have a kind of, if you consider its spectrum, then you have some space over this S line. And then at S equal to 0, we have the spectrum of this guy. And the other side, we have a spectrum of this guy. And so we want to show that this actually gives you, it's kind of flat family. And so this. So, but more precisely, somehow, as I said, we use algebraicization. So we use algebraicization. So I don't know. It is appearing or not. But anyway, so instead of this, we consider this. And certainly I have to take a closure. And also here, I have to take this. Maybe take this. And then I forgot about this. So just everything over lambda now. And here, here I also consider just a polynomial, and then polynomial. But yes, and like something like this. Closure is always necessary to take. So if S equals, so this is you may just think that this is it is a family of spaces. So at each S we have a zero-dimensional variety. I mean zero-dimensional scheme. And S equal to 0, you have this, and S equal to 1, then you have this. And so somehow we want to, roughly speaking, we want to know that the cardinality of points doesn't change as S changes. So some sort of flatness over this lambda S implies that this rank of this guy, so rank of this guy, y1 plus minus 1, yn plus minus 1, and modeled by p1, p and closure is equal to the rank of the same thing, like y1 plus minus 1, yn plus minus 1, modeled by dpo dyi, and maybe I have yi, and then b here, and then take its closure over this field lambda. So this is the statement. So I cannot really explain this so much, but I just want to tell you that we use the work by Markgraf-Tolman here, and then doing this. So what we have is this. So we have this lambda 0. We have a quantum cohomology of X with lambda 0 coefficient going to this Jacobian ring of this P of X. Right? And we know that this is surjective. And this is lambda 0 algebra homomorphism. And we want to show that this is injective. So now I just take quantum cohomology of X with lambda. Maybe better to write lambda 0 tensor lambda. And then this side also we want to consider the like this. And so we also have to show that this one has no lambda 0 torsion. So actually this is free over this. But then because the ranks are the same, so the ranks are the same rank, so they have they are same rank, then because this is surjective and rank are the same, this is a linear space over field lambda, So therefore, from here, this one is actually injective. And if, we know that if it has no lambda 0 torsion, certainly this one is also injective. So therefore, we show that this Kodaira-Spencer map is an isomorphism. So a little bit complicated, but somehow this is the way to show this. Okay. So then, finally, I want to tell you about a little bit about pairings, which I somehow mentioned before. It's about pairings. So here you have a quantum cohomology, maybe over lambda or even lambda here. So here we have a Poincare duality pairing. So the quantum cohomology is same as cohomology as a module, as lambda 0 module. And so here, if you have alpha and beta, then you can talk about just this integration by this. Right? So this is a pairing. And so, but for this one, this is isomorphic. So therefore, what kind of pairing do we have on this side? So I just want to discuss it. But in fact, we can discuss the semi-simple case. So what is semi-simple means? So semi-simple means that in our case, actually quantum cohomology is a finite dimensional things. Yes. So therefore, if it is isomorphic to the direct sum of lambda, because our lambda is, in our case, it's algebraically closed. So this is in our situation. Therefore, in this case, semi-simplicity means that this one is isomorphic to the direct sum of field lambda, right? So, okay. So then we call it semi-simple. And this condition is equivalent to say that the all critical points are this d square PO d yi dy j. Maybe I just multiply yi yj. So we consider such a Hessian matrix. Then this is non-degenerate. For all clear points, for all critical points, this is the Hessian is non-degenerate there at critical points. So this is a condition, right? Because this side, if it is just decomposed to one-dimensional things, that means this thing is actually non-degenerate. Okay. I just briefly explain this. So, okay, maybe I start from the conclusion. Okay. So quantum cohomology of X with maybe lambda coefficient is actually decomposed into several things, right? Lambda. And this one is isomorphic to my Kodaira-Spencer map to the Jacobian ring of this potential function. And then in this side, actually, we also have one-dimensional things. So maybe I just denote Z by Qj. And here I denote this as a direct sum of J and Jacobian ring and potential function X, and then Yj. So Yj is this critical point of this potential function. And this, it means that this is a homomorphism from this Jacobian ring to this lambda as a lambda unital lambda algebra homomorphism. Right? So we consider this. So maximum idea corresponds to the critical point. And so I take such critical point and then I just take. So this is actually just a decomposition into local Artinian ring. It's one-dimensional. And here I have this Qj. So Qj, maybe better to write it Poincare dual cross Qj. Qj is a cycle here, but anyway, so I just write this. Okay. So that means some Qj is an idempotent. So one, the unit here is the sum of Qj. Maybe it may be j equal to 1 to, I don't know, maybe I want to b, because it's a sum of Betti number, like this. And if you have a different factor, then the product is 0, right? So Qj, Qk is equal to 0 if j and k are not equal. And certainly Qj must be equal to Qj. So this is idempotent. So this is idempotent with respect to quantum multiplication. So sometimes we use such a thing in constructing certain spectral invariant. But anyway, so this is the one. And here I have also this unit of Jacobian ring. And this one is a sum of, maybe I just write 1 yj, right? So like this. And certainly here 1 of yj and 1 yk is equal to 0 if j is not equal to k. And 1 of yj and 1 yj is equal to 1 of yj. So it's a unit in this factor. Okay. So Qj and this 1 yj are related by the Kodaira-Spencer map. So this Kodaira-Spencer map of Qj is equal to this 1 I of j. Okay. And then what does it mean? So, but Kodaira-Spencer map is something coming from this Q maps. Right? So this is something related to these Q things, right? So this Qj of, yes. So how can I say this? Yes. So somehow this one is somehow related to this. So now, actually it may be a bit complicated, but somehow we can also consider bulk class here and bulk class here. and bulk class here, and so on. But then here, maybe I have to use some this like this. So this one is somehow this Q of B tensor L tensor Qj and something, and then maybe something like this. Well, maybe I have to put this Qj in a bit point, but somehow this one is something like this. So if we want to have this bulk deformation, then certainly we have this. But just forget about this. So the things maybe goes very similarly to this. So for simplicity. Okay. So then this Q of B Q of Qj is an element in this. Sorry. Maybe I have to write it more carefully. Okay. So I have Y. Then Y is actually Y1 Yn. And then last time I mentioned that you can talk about the variation of it. So this is just a variation of this Y1 variation of Yn. And then maybe you can also write it as U1 Un. And then we just define xi as just kind of logarithm of this t to minus ui of yi. So this has variation 0, and so you can think of its logarithm. It is not well defined, but we define up to multiple of 2 pi. And so adding multiple of 2 pi. So we have this. And then b y is maybe sum of xi and ei. Yeah? So this is a bounding constraint. And then so this one precisely what does it say? So it says the following. So at least you have this q here, and then you have this q here, and then you plug in arbitrary number of b's. And then sum them up, right? So here is k, and then maybe k. And then this one is actually the unit things. So unit means this is 1 of L ui. So here is a constant function y, but somehow so this one doesn't really play any role in this function, because it is a constant function 1 on this Lagrangian torus fiber. But anyway, I also want to indicate this. Okay. So this is one. Okay. So then if you look at the following things, so like so this q of this q and by by, and then here I take a volume form of this one, or maybe it's a Poincare of the point class, and then this one is equal to 1, right? So 1 and volume, and then take a wedge product and integrate. So this is a unit volume, then it's 1. Right? So what is Q? So Q, as I said, here I have so in this case I have only one input, right? Only one input. If we have this yellow B, then we have other yellow mark points. But I only consider equals to 0 case, so therefore I only have one thing. And then here I have one boundary mark point and k many mark points, so they're like Z0, Z1, etc. Zk, and then take a evaluation here, right? So this is sorry. No. evaluation here. So this is a Q map. So this is input. Yeah? So here I insert Q and then do this. So this is actually our Q map. But you can also think the following thing. Here you have a disk, and you have a bunch of map points on the boundary, and all of them are now, so Z1 to Zk are all kind of inputs, right? So here now all boundary map points are input points, and then if you consider interior map point, which this one is output, right? Output point. So this one is our operator pay. So pay is a map from this, in this case actually maybe cohomology of X, tensor L, tensor cohomology of L, going to this cohomology of X. Right? Maybe I need to use this lambda zero coefficient everywhere. But anyway, this is a pay map. So insertion is done at all the interior map, the boundary map points. And if we have other several map points, interior map points, we can also use them as input points. But there is one specific interior point where we think of it as output point. So therefore we have this one. Right? But these two things are kind of dual. So therefore, this one can be written as Q here and pay here. And in this case, I have only this. So By, tensor By, and maybe this last one. So this is a pairing in this LUY, and this is a pairing on the ambient space X. So Q is a cycle, maybe Poincare, but cycle in the ambient space. And pay, the output of pay is also a cycle in the ambient space. So therefore you can take the Poincare pairing on the ambient space. So we have this. Okay. So let me just denote this pacing following way. So maybe for this one, I may just write it Byj of this point, the volume form, volume class is by definition this pay of, sorry, this is B, small by, Byj, tensor K, sorry, then I have to sum them up, sorry. And then maybe, yes, so maybe I have to write this way, K tensor this, and then somewhere I have this volume LU, and then maybe Byj, and then maybe tensor K2. So I think this way. So maybe, yeah, so sorry, this is not the bold one. This is actually just By. I have here, this one. And then maybe I was wrong that this one can be put anywhere. So maybe, because here we have to consider the cyclic order here. So therefore, so here I have By, and then By, sorry, By, something like this. Okay. Because, yeah, in this case, actually output is volume, but then we don't know. So this. Okay, so maybe this way. Maybe if we have a cyclic symmetry, then you just take one of the terms, but otherwise, okay. So therefore, what I said is that 1. So this is 1, right? So 1 is equal to this Q, J, and this P, By, J of volume of L of U. Sorry, so this is Uyj. Sorry. So this is also L of Uyj. Okay, but anyway, so like this. Okay, so Qj are element like this, right? And for quantum modification, if you have these three things, alpha, beta, gamma, and then this must be equal to alpha and beta, gamma. So you have this sort of things, because if you remember the definition of the quantum cup product, then actually we define some sort of structure constant using 3-point Gromfit invariant, maybe actually third derivative of Gromfit potential, and then certainly this sort of thing. So anyway, you have this. And so therefore, if Qi, so if you have this Qj and Qk, right? And then certainly you can think of it as Qj and Qk and quantum modification with a unit here, right? And then you can just put it this way, Qj, Qk, and 1 here, right? But this one is equal to 0 by this. So therefore, this one must be 0. They are mutually orthogonal. And similar thing also from this. So from these things, actually we can see the following. So P of B Yj of this volume of this Luy J is equal to multiple of this Qj, but there are some scalar that is this. So somehow we have these things. And we want to know these things, right? Because here I have Qj, here I have this 1 Yj here, right? I already noticed that they are mutually orthonormal, right? Orthogonal. So therefore, they should be orthonormal. So then what we have to know is the norm of this. Then if we set the norm of this same as this norm, then certainly this gives you isometry. Right? So therefore, we want to know, so in order to define pairing this side, on this side, so we define it is equal to 0 if j and k are different. So we want to know this 1 yj and 1 yj. And then it should be this qj, right? Next. So therefore, somehow we want to define this. We want to compute this. So finally, you may find a little bit interesting geometric construction. So I consider this and the volume of Lu Yj, and then pay B Yj of volume of Lu Yj. So I just take a self inner product, and then this is equal to this. So therefore, it is actually a self inner product of this guy, and then square of this. So therefore, what you get is 1 over Qj, right? Like this. So we want to compute this Qj, but Qj is equal to 1 over this. So here you don't, I don't need to write it so much, but this volume and P of Byj of volume. So if we can compute this, then we are done. So we want to compute this. Okay, so now some geometry. Now some geometry. So what is P? So P is actually defined this way, right? So again, I just draw the same thing, but so I insert this Byj here, Byj, sorry, it's not bold. So I insert and so on, and then I want to take a output here, right? So this one is the image is actually this Pyj. So we want to consider the kind of self-intersection number of this. So now I consider following. So here I have this thing, and then maybe here I have manifold X, and then I don't know. So maybe there are some Lagrangian here. And then I want to consider something like this. So here I have something, and then going this way. And so this is a holomorphic map. Maybe U. And then I have a bunch of mark point here. So therefore, I have a bunch of mark point here. But then I have a 1 point here. Then I take a variation at this point, right? So we also consider another one here. Maybe from here to here, like B here. And then I have also some mark point here. And then I have also output here, right? So then we may have other one like this. And then output is here. So I have two. So I consider the moduli space of such a thing. So therefore, in the image, actually, this evaluation image actually moves inside of manifold. So this gives you some cycle here, and also you have something similar to here. So we want to know their intersection number. Therefore, what we look at is the following. So we want to know the following things. We want to know this and this. So this one lies on LU, maybe LU. And this one, in this case, also lies on the same thing. So I don't know, maybe they are connected somewhere. But anyway, we want to consider this sort of configurations. So here I have a bunch of mark points, so therefore I consider iterative integral of this side and this side. So it gives you some weight to the intersection number. But somehow what we have to count is how many such configurations exist. So we want to somehow count this. So when I discussed this Kodaira-Spencer map is a ring homomorphism, I consider certain moduli of disks with 2 interior mark points and 1 boundary mark point, and then consider some 1-parameter family and so on. So here we also do something similar. But here actually now this interior node, you look at this interior node, and then you smoothen this. Then what you get is certainly this. Right? So smoothen this, then what you get is this. So what you get is this, just annulus. Okay? But we have one special thing because we consider this Pyj of Pbyj of volume. So there is one specific thing here. So among many boundary mark points, actually we have some specific mark points on each boundary component. So they actually correspond to the volume of this. Others are just b's, right? Okay, so here is one thing, this is actually one thing here, and then one thing here. They correspond to volume form. Okay? So if you consider Poincare dual of it, so volume is something like a Poincare dual of the point class. So if you want to count object, then this is actually a point here. And here you also have a point here. So this is a Poincare dual to this. Okay. So volume or maybe point, Poincare dual point. Okay, so anyway, I have here some specific mark point here and there. So now I consider, just these things. Maybe I don't know, maybe somewhere like this. We consider the moduli of this. And so before doing this, maybe you should just consider just annulus. Certainly you know the modulus of annuli because it's kind of if you normalize this size and then maybe the length, maybe the modulus, but it has symmetry. It's a rotational symmetry, so therefore it is not really stable object. But if you put one mark point here, then you don't have rotations. So this one is a rigid, this one is a stable object, and the moduli of such a thing is actually isomorphic to the, I think this real line. So it may be getting longer and longer, or maybe getting thinner, right? So that's the kind of modulus. So this is like this. And if you put another mark point somewhere, so if you consider moduli of another one, so I should keep this. So if you consider moduli of this guy, and this one and this one, if you consider moduli of this guy, and then this guy is actually isomorphic to R cross S1. Because now you have to know the another point, and then it is flanked by, it moves on the circle. So therefore, this is R cross S1. Okay? Okay. So now we consider the two special objects there. So one is I already wrote. So this is this kind of object. And this is actually a rigid object because here is a node, and so no relative positions because it's split into two components, and then this is actually one point. Okay, and the other one is maybe I have to draw it certain way. And this, and this. So this is also rigid object because you have three special points on each component, right? Here you have this boundary two boundary nodes and this boundary mark point. Here also you have two boundary nodes and one boundary mark point. So therefore this is also rigid object. And if you smoothen this, then you come to this. Right? And if you smoothen this, then you also come to this. Right? You just smoothen this, what you get is this. Right? Right? So here, if you smoothen this, right? So if you smoothen this, and that's what you have this kind of stuff. And so this is the kind of smoothing node, and this smoothing a node, and smoothing two boundary nodes. So this is actually, you have a two parameter, and here also one each. So therefore you have two parameters. Okay. So then we can consider such a path. Okay. So again we have a path in the moduli space of this annulus. So here I consider moduli of annulus with boundary mark point on each boundary component with a boundary mark point on each. So we consider such a thing. So this is actually, as I said, this compactification of this R cos S1. And then we have to compactify somehow. So maybe if I compactify again, I get a disk. But anyway, so before compactification, I have this R cos S1, but somehow we have to compactify it, right? And then this one contains these two things. This one contains these things, right? And this one also contains these things. Okay. So now I consider some paths. Maybe again I pass. So it's an interval joining these two things, and then consider the following things. Basically, what we consider is the following, right? So I have this, and then map to x, and then here is some Lagrangian, and then we have these things, right? So yes, it may be map W and this holomorphic map, and then if I have two map points here, then we have two map points somewhere here and here, something like this. And maybe if I have other map point here, then maybe like this. Okay, so something like this. So we want to count this, right? But then again I consider this interval, and then inverse image of I from this moduli space, right? So then this one is equal to maybe the numbers of holomorphic maps, so that number of maps. So I cannot write the image of this, so therefore I just write in this way to this x and w holomorphic map, and I need to put some mark point. So here I take a point here, then maybe I take a point here. No, sorry. I make a I take a I have to specify this point. So maybe I have here some point here, and I have some point somewhere here, and then I have another point anywhere. Right? But they are all B's. B is codimension 1, so therefore, how many mark point can be mapped to B is actually, yeah, just a topological thing. So therefore, yeah. But anyway, so you can choose, yeah, number of intersection points, and so you may consider this. So somehow counting this, you reduce the counting of this. Okay, and then you may realize this, that there is some infinity structure appearing here. Namely, if you just forget this, then if you think of it, if you have some element here, and then you think of it also input, right? Input here, input here, input here, and so on. Then which way? Yeah, starting from here, yeah, input here, input here, input here, and so on. Then in the end, you have output here. Similarly, you have input here, and so on. Then again, you have an output here. And then you want to see the intersection number there. So, okay. So in this way, so this one is equal to the following. So maybe I have to write it more precisely and with some signs, but maybe I just write it in the following way. So this I1, I2, and here I have this M2 of B of Yj, and E of I, and here maybe I have volume here, and also here I have M2 and Byj and E of j and volume, and then take a product inside of this element. So there are some of I1, I2. What does it mean? So somehow so this is the intersection point, right? Intersection point. So I have now L times L, and inside here I have a diagonal, right? Diagonal. And this diagonal is actually homologous to this, right? So this GI1, I2 of this EI times EJ I2 or something. Maybe we need some sign and then sum them up. So this EI1 and EI2 are actually basis of cohomology or basis of homology. It depends you are working on homology or cohomology. But so the diagonal actually homologous to the cross product of certain homology classes of this L. So in fact, this actually is a coincidence condition here. Coincidence condition means that if you consider these two maps are maps to x cross x, and then here this map point is mapped to this diagonal. But in this case, actually, diagonal is homologous to this. So therefore, instead of this, we just plug in this. So here actually plug in this and plug in this. So this side or that side, and then we get this. Okay. So next, I consider maybe I already spoke too much. So anyway, so what I said is the following: so H of this Lu Yj, maybe over lambda, and it has a product. So maybe if I take here from two elements like A and B, and then I want to define some sort of product. So this one is actually defined up to sign, defined up to sign this M2 of AB. I explained that you have this DGA, and then you change sign, you get the infinity algebra. Yeah? So from DGA, you get the infinity algebra. That sign appear here, so that it's converse way. So here you have a M2 then from M2, you can define some product structure in this situation. And then this is algebra. And so then the following thing is true. So EI, so E1 to En, a basis, integral basis of this H1 of LU of this with integral coefficient. And then what we can see is this one, yeah, plus EJ, EI. So this sort of stuff. And this sort of stuff is equal to this, d square PO of dxi dxj at this point byj. And this is equal to this yi, yj, and d square PO, and dyi, dyj at this yj. Yes. So this is actually, I already mentioned, this is actually due to Cherry-Finchou. This is observation by Cherry-Finchou. If you differentiate potential function twice, then you will get M2 of EIEJ. And so therefore you have this. So this is actually kind of Clifford algebra. So now change coordinate. So now change basis. Change the basis. And so that in new basis we have this EI, EJ is equal to 0 for IJ, and EI is equal to half of this square of dxi dxj byj, or maybe half of yi yj d square PO dyi dyj at this yj. Okay, so we change the basis and do this. Sorry. It is 0, I, so then, sorry. This one is second derivative of this, sorry. Second derivative of this. And this is also second derivative of this, and then maybe yi squared. So it's like this. Yeah, because here, if I equal to j, so EI is equal to something. So therefore, you have 2 times EI is this component Hessian. So therefore, if only have this, then I have this, just half of this. Okay. Then I want to compute the thing like M2 of Byj of EI 1 and sorry. Then this volume things and M2 of Byj of EI2 of volume things like this, and then take I have GI1 and I2 and then some sign like this. But somehow this volume is somehow in this case maybe E1 rather than En, right? Something. At least the lowest order terms, actually you have this. So now you have this. But then you have a kind of, this is actually Clifford algebra. So somehow this one is something proportional to this E, I don't know, so E I1 complement. So sorry, I is a subset of this 1, 2, n, right? And then I maybe I don't know. I may be I1, I2, IP, right? And then I denote by EI is equal to this EI1, it's a product of this thing in the Clifford algebra. So just take these numbers and take corresponding vectors in the H1 and then just multiply by Clifford multiplication. And then you have this. And if you have this, so here you have, say, E1, and then here you have E1, En, right? Then this gives me a scalar, right? Just a component, the entry of Hessians. And then we have rest E2 to En, right? If I have E1, E2, and then here I have E1, E2, En, then first we just flip these two things, this minus E2, E1, and then E1, E2, and so on. Then you multiply this, then they become scalar, and then multiply this, then they become big scalar. So therefore, only this E3 to En remains. So somehow we have this complement of I, but we also have a scalar in front of it. Okay? So maybe just to let me denote this EI is equal to DI. And then this one is after the product of DI, where I is inside of I1. Right? And then maybe some sign may be arise here. But anyway, so here we also have the same thing. So this is the product of J inside of I2, and then DJ, and then E of I2 complement. So now you have this EI1 complement and EI2 complement. But then, because we have this sort of compatibility with multiplication and inner product, so therefore this one must be this EI1C times EI2C, and then maybe just unit here. But unit is this is just a constant function 0. And so we are using Poincare pairing, so therefore here we need a volume form. That is, we need to have E1 to En somehow. We need E1 to En. Otherwise it is trivial. So therefore, this one is somehow equal to 0. So equal to plus minus 1 or 0 if I1 union I2 is equal to, I1 complement I2 complement. I1 complement I2 complement is just equal to, I have to say, maybe better to say this. So I1 C and I2 C. Maybe I think so. Yes. So this one must be a disjoint, and maybe so union must be whole thing, and then maybe disjoint. And otherwise maybe 0. So somehow the only remaining part is actually when these are complementary. So therefore we take a pairing of this, and if then that case actually I1 is I1 is a complement by 2. So therefore here this one. So I2 is a complement by 1. So therefore here this one is equal to basically the product of DI for all I. and then other term may not contribute. Something like this. So maybe some computation is not so precise, but how many terms appear here? How many terms appear here? So if I pick I1, then I2 must be its complement. So therefore, it's only enough to consider the possibility of the I1, right? But certainly the I1 inside of this. If you take its cardinality, and then this one is just 2 to the power n. Right? So therefore, we have 2 to the power n component. So therefore, in fact, this one is something like 2 to the power n, and then the product of this. Okay, but because this one is this one, so two times. So yes, this because this one is this one. So therefore, two times of this and this. So 2 times di is equal to this, and then of diagonal term is 0. So therefore, 2 times product of di, I equal to 1 to n, is exactly equal to determinant of Hessian of this derivatives. Something like this. But as I said, so in general, yeah, so this may be only lowest order term. So therefore, at least they are actually equal when up to this lambda plus or something. So in general, it is not really the case, but we know that this qj is equal to this 1 over the determinant of Hessian of Hessian of g square p of dyi dyj yij, and then take value at yj, something like this. So this is actually the conclusion. Yes. So maybe modulo lambda plus. And in fact, I'm cheating many things. So here actually I use some sort of symmetry of this product structure and inner product, so-called cyclic infinity structure. And so therefore it is not the infinity structure I constructed before. And for that reason, somehow this computation is okay, modulo lambda plus, but yeah, not really equal in lambda. But in Fano case, and Barak class is degree 2, then actually it is actually equal. So there are some cases we know that this is equal to this, but so like a Fano case, and then degree of this one is equal to 2, I think something like this, then this is actually, it is equal. Otherwise, we may have a difference. So m, k things, this b, yes, b, and also maybe I deform by this by something, yeah, may not be cyclic infinity structure, and then as an infinity structure, actually this is equivalent to the original one, the previous one, but not equal. So in such a case, actually we don't know whether this is not really equal, I think. So anyway, so this is again, and so the last time I picked the case of CPN, and then look at the Kodaira Spencer map, but not not the way I explained today, but exactly zj is mapped to certain monomial of yj, and then we know exactly what correspondence of quantum cohomology element and the element in Jacobian ring, and also we compare the pairing there. So then we also observe that this is actually Hessian. So that story can be extended, but a little bit complicated way. Okay, so this is almost the story I wanted to tell. But finally, I just want to mention little observations. So one thing is this. So one is actually estimate for displacement energy. So if you consider Hamiltonian function, like maybe I just consider 0, 1 cross x to r, and then we may denote by h over is just the integral of oscillations. So maximum of ht dot over x minus minimum of ht dot over x, and then integrate over t. So if we have phi, which is Hamiltonian diffeomorphism, then we may also denote this the same letter. I don't know if this is good notation or not. This is actually the infimum of all possible Hofer, the Hofer norm of all possible Hamiltonian functions, so that this phi becomes time one map of this. Okay. And then if you have L inside of x omega, right? And then certainly the Floer theory may not be zero, but we know that this can be anything. So this maybe A is just some compact set, closed set. And then I consider the displacement energy of this as this. So this is the infimum of phi, so that phi of A is disjoint from itself. And so it is infinity if no such phi exists. So this is the displacement energy. And the fact that one of the theorem, maybe it may be noticed by many people. I don't know. Maybe it may be noticed in some cases by Porterovich, and then Tsekhanov, that if L is in x omega, and this x omega may be a closed manifold or tame symplectic manifold. So nice boundary, and if it is also closed, compact without boundary, maybe compact without boundary, then displacement energy is always positive. And what Tsekhanov proved is the following. So what Tsekhanov proved is the following. This EL is at least the following things. So this is a little bit complicated, but maybe roughly speaking, you take infimum over all J, which is maybe tame symplectic structure with omega. So this tame is different from this tame, but anyway. And then take not the infimum. Here it's a supremum. This is a supremum. This is a supremum. and then take an infimum of the following things. So now you consider the area of this where U is a holomorphic non-constant map. So he proves this. In fact, in his paper, he also considered this he also considers this. But the important part is this. So if you have holomorphic disk, then you look at this area, and then for non-constant holomorphic disk, then the area actually has a lower bound. I mean, strict lower bound. Yeah, it's positive lower bound by Gromov compactness, and then even you can take a supremum of this. So therefore, you get some positive number. This is actually Tikhanov's. And this thing is actually he proved it by using a kind of variant of Floer theory. So if you can avoid bubbling, and then up to that point you can define some Floer complex. This is not really precisely, but so then you consider such a lower bound, lower energy Floer theory, and then maybe you can do it. But in fact, in our case actually we can also do the following. So let's suppose that you have this thing. And for simplicity, I assume that we can define Floer cohomology. In general, we cannot. But anyway, yeah, in such a case, we may also consider the lowest order, lowest energy obstruction class, and then do something. But let's suppose that this is actually unobstructed. Then we can define Floer theory with itself. But usually we consider coefficient over lambda, so Novikov field. But we can also define Floer theory over lambda 0. And lambda 0 is kind of positive part of formal power series. And so then this one is actually always isomorphic to the following type. So lambda 0 plus n plus lambda 0 over t to the power lambda k of lambda 0, and maybe k, I don't know, 1 to, I don't know, anything. 1 to a or something, anything. So we may not have any torsion part. But so free part and torsion part. Yeah? So if n is positive, then certainly the Floer theory over LL lambda is isomorphic to this lambda with n. This is non-zero. And Floer theory over lambda is invariant under Hamilton isotropy. So therefore, in this case, L is non-displaceable. So therefore, you have no such thing so that displacement energy is infinity. But if n is equal to 0, then still we have this part. And so in this case, this Floer theory is 0, but our displacement energy is actually bounded from below by a maximum of this lambda k. So maximum exponent of this guy. So maybe I have no time to explain the proof, but I can tell you one thing. Okay. So let's consider P1 plus P1. But maybe first factor is omega, but second factor may be k times omega, right? So k is some positive number here. Okay. Then we can draw this picture like this. And so if you pick some point here, then there are 4 holomorphic disks, like this one, or this one, or this one, and this one. Right? If this one is not in this case, if this one not in the barycenter, actually you can easily show that this one is displaceable. You can displace, so except the central point, actually this one can be displaceable. But if you compute the self-intersection Lagrangian Floer theory, then one of the exponent must be one of these, the affine length of those things. So Chekhanov theorem says that this one is infimum, right? Infimum. So therefore, he look at the smallest affine length. Okay? So now you have this, and then just consider big point. I consider k is bigger than or equal to 1, right? So then this one. And now you take this point. Right? And then here you have this and this, they are equal. Okay? But maybe better to draw it a bit bigger. Right? Okay? And then actually in this Floer theoretic torsion is actually coming from length of this. So this actually gives us a torsion exponent of this self-intersection things. So this one may be bigger than this. It depends on location. Yeah? So if you look at the smallest possible area of the holomorphic disk, then you find this as the smallest area. But somehow these two cancels in Floer complex. So therefore, they don't really appear in the torsion exponent of Floer theory. Instead, this one appears in the torsion part. So therefore this estimate somehow gives you a better estimate than this well-known Chekhanov result. So this is one thing. Okay. So maybe I use a little bit more time, but so the last thing is about, this also maybe already, I don't know, a few years old, but maybe I can tell you the same thing. This is baby version of generation criterion. Okay, so for instance, I consider CPN, and then we have this thing. Okay, and then say we have, if n equal 2, we have this as a momentum polytope, and then I have this point like 1/3. Over here we have a non-displaceable Lagrangians. So I have this L of U naught. And there are 4, in this case, sorry, not 4. In this case, actually we have n plus 1 critical point of this potential function of this LUZ. So we have n plus 1 critical points. And okay, so this is equal to the sum of Betti numbers of CPN, p equal to 0 to n. So this. Okay. So now I want to show the following. So, okay. So I want to consider the following map. So we consider this map quantum cohomology of, say, CPN. And then going to this Jacobi ring of these things. And this is maybe we define by using the spacer map, but I told you this is something related to Q map, because the MK operator is defined by using Q operators. And so using Q operator, you can describe Kodai spacer map. And we know that this is actually isomorphism, right? So somehow, okay, so now I have this quantum cohomology of CPN and lambda 0, but this one is a direct sum of, sorry, maybe I just, any is, okay, so lambda 0 times this Qj, right? So J, in this case, maybe J is from 1 to n plus 1. And here I have a Jacobian ring. So this one is also isomorphic to direct sum of this Jacobian ring, P of CPN and Yj, and J is from 1 to n plus 1. And so somehow we have this. And I somehow, when we discuss this pairing, somehow I mentioned the following. So this Qj is equal to this Qj of 1 of this pay, sorry. Which one is correct? Pay of By of volume form is equal to this times Qj, right? So this I mentioned before. So somehow this one is this. So volume is Poincare dual of the point class, right? Okay. So now I just draw this. So I have several things, but I have this volume form for L of this U0. But for each Yj, the critical point, we can consider P of B of Yj. And then this one is equal to that, right? So this is actually, I'm writing it again. And so therefore, if you just multiply this, then this unit of this is actually written as a sum of this Qj of this P Byj of volume of this LU0. So this is equal to this. Okay. So on the other hand, we have a map from this to any unknown flow theory. Maybe I may have some bounding chain, so therefore I may have some bounding chain here and then I may have this bounding chain here. Okay, so let's suppose that K is unknown Lagrangian submanifold with the weak bounding chain, or maybe weak Maura-Cartan element, this BK. Okay, so we have something like this, and let's suppose that this Floer theory of this one. Sorry, it's not necessary right now. So you have some unknown Lagrangian, so that it admits some weak Maura-Cartan element here. Then we have map like this. Maybe sometimes I rewrite it as I star of quantum things. So this K, so we have a K inside this X, right? So somehow, yeah, we have a, yeah, just a kind of pullback map, right? Something like pullback map using quantum things. So therefore I have this. So how we do this? So this is exactly our Q. So I have one into the mark point, and then I just insert this A, right? So this is actually Poincare ideal across A. And then we consider this thing, and then maybe I just consider the aberration at boundary mark point. So maybe I have a bunch of things here, so that they are all By. Or BK. All BK. So this BK. Okay? So this actually on this unknown Lagrangian K. So this one is actually Q and Q and A, and then BK tensor K, and then sum them up over K. So like something like this. You have this map. And one fact is that if you consider the quantum pullback of the unit here, then it goes to the unit of Floer theory. So this K and B K in this Floer theory. So this is actually more precisely, in fact, only contribution coming from the constant map, and then the only thing is this. So this is in fact a proof. Okay, so we have this. Okay, and then what do we have? Right? In fact, what we have is this. So here I have some Lagrangian here. This L of U Yj. And then I can just consider something because this, if you consider some of them, then you get a unit, right? And then here you consider this. So somehow you have this picture. Maybe I just draw this again. So I have a Floer theory of this L U Yj, Byj, and L U Yj, Byj. Yes. And then from here to quantum cohomology of X by using our pair map. So I have a, so pair map is, again, I just remind you what we use. So all the boundary mark points are used for input, and then take a output at some interior mark point. So therefore you have this. And in particular, this is spacing, right? So here you consider sum of this Qj and volume of L of U0, right? Sorry, volume L of U0. So we consider it an element in this HF of L of Uyj. Yeah? Uyj. Something like this. So I want to take a sum, so therefore I have to take a sum here. Then you have this map. So each component we have this map. And then this one is mapped to unit here, right? So something here is mapped to unit. That is this formula, right? Okay. And then we have this fact. So I just erase this picture, and then I wrote it like this. 1 of x goes to 1 of k bk. Okay. So I have something which is mapped to unit, and the unit is mapped to unit here. Okay. Okay. And then I have a theorem. If this one is non-zero over lambda, then this k must intersect with this. So this k is unknown Lagrangian, but if you know that this unknown Lagrangian has non-vanishing Floer theory, and then this such a thing must intersect with Clifford torus, monotone Clifford torus. This is a theorem. And in other words, it says that if this one is a non-trivial object in scalar category, and then it must intersect with this. And the argument is, you may already see. So here I have this L of U0, and then I have something like this. Maybe here I have to put a volume form, maybe as a Poincare point glass. And then we may have a bunch of points. And here I have this output. But then this output is used as an input, and then you have this. Because this one is going to this, so therefore something, in fact in this case, something must exist. So the point is, Floer theory is non-trivial. If this is non-trivial, then certainly unit is non-trivial. If Floer theory is trivial, then unit is equal to 0, because this is 0, so therefore no non-trivial element here. But if this one is non-trivial, then unit is non-trivial. So therefore, there must exist such a thing. There must exist such a thing. Okay. And here, it's a unit. So therefore, if we want to consider the pairing with the target, and then maybe here again I take a point class. So somehow this kind of cardinality is non-zero, right? And then we use similar argument, this what we call annulus argument, or some physicists may call it Cardy relation. Which is the argument I already explained before. So this one actually tells you that the number of this thing is non-zero. So here actually still I'm cheating a little bit, but so maybe I have to be careful about this. So here I have this boundary map to this L. And then I have another boundary which is mapped to K, right? So now I have a annulus, and one of the boundary is yellow here. Another boundary is blue, like this. And then look at the boundary, and then yellow one is like this, and blue one is like this. Okay? So this is a proof. Because yellow one has to map to LU, and blue one has to map to K, right? Then you consider this point. Here, actually, this point has to map to yellow one because this is a point on this yellow one, right? But this one also map to blue, the K because it's on the blue one. So therefore, from here, if we know that it is non-zero, it is non-zero because this kind of composition is non-trivial. So therefore, you need such a homomorphic map. And then this number is equal to this one. Then we know from here, because this is non-zero, therefore we have this LU0 and K must intersect. Okay? But still I'm cheating a little bit. So the point is that if you consider such a kind of deformation, then we have to always worry about the disk bubbling, because disk bubbling happens in codimension 1. So during this thing, maybe you may encounter with some other kind of things like this. Then maybe moduli just finish there, right? But bounding cochain or weak bounding cochain is just designed to overcome such things. So we have to show the one of the things like this. So if you have this, then we may also need this. So that means if the potential value of yellow one is equal to the potential value of blue one, then actually boundary contribution somehow cancel out. So when I define this Lagrangian interstitial flow theory, here I have this L1 and B1, and here I have L2 and B2. If the potential function, the value of potential function B1 is equal to potential function of B2, then we can define this. We have a differential. So we can rectify the Floer's boundary operator to Linear boundary operator. So this is because if you have this bubble this side, it may contribute to the boundary of the moduli space of strips, but that thing also happens in this side, and then these two effects cancel out. So here we have to also do similar things, and if then I say such a thing, then that's the end. So okay. So the key is this. So you have this quantum cohomology, or say now CPN, maybe lambda here, and then going to this HF, this KBK and KBK. So let's suppose that it's non-zero, right? So here, this one is actually direct sum of this lambda and qj. J is equal to 1 to b. And here you have this 1 of kbk. And then, so this is actually ring homomorphism. Yes. And so if you know that this qj is going to this some element here, sorry, maybe how to say. Yeah, what I want to say is that this qj and qk are, k and j are distinct, and then they actually goes to, so what I want to say is that if j and k are different, and then this qj and qk are equal to 0, so from here actually we can say that there is unique j, so that this, I wrote this I star of qj is non-zero, and yes, and then this one is equal to I of q star of qj is equal to this 1 of k of pj. So this is one. Okay. So now I want to consider the value of potential function. Yes. So I want to consider potential value of this thing, right? So this is the following, right? So this is the following. So you have one output, and then you have a bunch of pk's. And then just sum them up, right? So somehow sum over the sum of them like this. No, it's okay. So this is something like this. So somehow, yeah, we consider or yeah, I think. Yeah. Sorry. In this case, maybe I need more complicated argument. Yeah. That maybe I need a bit more complicated argument. So therefore, maybe this part is, yeah. I need, yeah. I remember. So this part is not so easy to explain. But what I can say is the following. So in fact. We can show the following. So there exists J such that this potential value of this K of Bk is equal to the potential value of this B yj. So here I have Lagrangian submanifold, which is a monotone Clifford torus, and it has n plus 1 critical point of the potential function. So the critical point of this, right? And then you look at this potential value of this critical value of this. And so the statement is in fact this HF of K of BK is non-zero. It is defined and this is non-zero. Then there is some J, so that this one is equal to one of the potential values. And so then actually, in fact, this Qj must be same as corresponding, the Qj must correspond to Yj. So that means here, actually I also put this mark point. So these mark points actually map to Byj. And here you have this Bk. And now if we have this, then kind of this effect, using this Byj things are equal to this kind of things appearing for Bk side. So therefore, so if you have this, then we can actually see that these two kind of phenomena cancel out. So therefore, still, even though you may have this sort of bubbling phenomena, actually this one, the number of this one is equal to the number of this one, and so therefore it is non-zero, and this one is non-zero. So maybe this is a, maybe you know this kind of argument. You need some care, but so this is one of the consequence of our story, and for generating criterion, maybe I have no time to explain, so maybe, I don't know, sometime. Okay, thank you very much.